space should be blindingly bright. Every direction you look should hit a star eventually. But the darkness of space is the single most important clue about reality. It proves the universe isn't eternal. It proves we're living in a cosmic accident that won't last forever. And here is a question. If you could witness any cosmic event in history, which would you choose and why? Comment down below. I will pin the most creative answer. Now let's begin. If space contains so many brilliant light sources, shouldn't the night sky be blazing with light? This isn't just a casual observation, it's a genuine scientific paradox that haunted astronomers for generations. They called it Olbers Paradox, named after a German astronomer named Heinrich Wilhelm Olbers, who wrote about it back in 1823. Though honestly, thinkers had been wrestling with this question long before Olbers came along. Imagine you're walking through a forest. If that forest goes on forever in every direction, no matter where you look, your line of sight will eventually hit a tree trunk, right? Every single direction, blocked by trees. Now apply that same logic to the universe. If space stretches on infinitely and contains an infinite number of stars, then every direction you look should eventually intersect with the surface of a star. The entire sky should be as bright as the surface of the sun itself. But obviously, that's not what we see. Step outside tonight, and you'll encounter darkness. Deep, profound, beautiful darkness. So what's going on here? Why does reality contradict what seems like perfectly reasonable logic? For the longest time, astronomers proposed various explanations. Maybe dust clouds between the stars were absorbing the light, they suggested. Maybe the universe wasn't actually infinite. Maybe stars weren't distributed evenly throughout space. Each theory had its problems though. Dust clouds, for example, would heat up from absorbing all that starlight and eventually start glowing themselves. That doesn't solve the problem. It just shifts it around. The real answer turns out to be far more profound than anyone in the 1800s could have imagined. It doesn't just explain why space looks dark. It fundamentally transformed our understanding of the cosmos itself, revealing truths about time, space, creation, and the ultimate fate of everything that exists. Before we dive into the solution, let's appreciate just how counterintuitive this whole situation is. Your eyes are incredibly sensitive instruments. On a perfectly dark night, adapted to the darkness, your eyes can detect a candle flame from about 30 miles away. You can see stars that are trillions upon trillions of miles distant. Light that's been traveling for thousands of years reaches your retina and creates a signal your brain interprets as a tiny pinprick of illumination, the stars you're seeing with your naked eye. Most of them are relatively close neighbors in our galactic community, hundreds or thousands of light years away. But telescopes reveal so much more. The Hubble Space Telescope has captured images of galaxies that are billions of light years distant. Each of those galaxies contains hundreds of billions of stars. We're talking about quantities that break our brains when we try to comprehend them. And yet, between all those galaxies, between all those stars, we see darkness, vast oceans of emptiness. The question isn't just academic curiosity. It's a fundamental clue about the nature of reality itself. Now, to understand why space is dark, we need to journey back to May 7, 1823, when Heinrich Olbers was putting the finishing touches on his famous paper. Olbers wasn't just some random guy speculating about the stars. He was a trained physician, specifically an ophthalmologist, who became absolutely fascinated with astronomy. After losing his wife and daughter, he devoted himself completely to studying the night sky from his personal observatory on the second floor of his home in Bremen, Germany. Olbers spent countless nights observing, measuring, and thinking deeply about what he saw. And that morning in 1823, he arrived at a troubling conclusion that challenged everything astronomers thought they understood about the universe. Here's what Olbers was thinking. Following the ideas of Isaac Newton and René Descartes, most scientists at the time believed the universe was infinite and eternal, stretching forever in all directions, existing for all time, unchanging. This made sense to them because if the universe were finite and just sitting there, gravity would pull everything together into one massive clump at the center. But if space went on forever, gravitational forces would balance out in all directions. The universe could be stable, static, eternal. But Olbers realized something didn't add up. In an infinite universe filled with stars, your line of sight in any direction should eventually land on a star's surface. Think about that forest analogy again. In an endless forest, everywhere you look, you see a tree. In an endless universe filled with stars, everywhere you look, you should see a star. Now you might be thinking, wait, but stars farther away look dimmer, right? So maybe the distant ones are just too faint to see. That's actually a really smart observation, and it's what a lot of people initially thought. It's true that light follows what we call the inverse square law. If you move twice as far from a light source, it appears 4 times dimmer. 10 times farther away, 100 times dimmer. But here's the clever bit that makes the paradox so stubborn. While individual stars get dimmer with distance, the number of stars increases with distance too. Imagine a sphere around Earth. If you double the radius of that sphere, the volume inside it increases by 8 times. That means 8 times as many stars. The dimming effect and the increasing number effect actually cancel each other out perfectly. Let me put it another way. Imagine you're sitting in the center of a giant spherical shell of stars, all at the same distance from you. Each star contributes a tiny bit of light. Now imagine a second shell, twice as far away. Each individual star in that distant shell appears 4 times dimmer. But there are 4 times as many stars in that shell because it has 4 times the surface area. The total light from the second shell equals the total light from the first shell. Keep adding shells farther and farther out, and the light just keeps adding up. In an infinite universe, you'd have infinite shells contributing infinite light. The sky should be blazingly, unbearably bright. Every point in the sky should glow with the intensity of a stellar surface, but it doesn't. Obviously, it doesn't. So something fundamental must be wrong with the assumptions. For decades, this paradox gnawed at astronomers. Some suggested that perhaps the universe wasn't infinite after all. Maybe it had edges or boundaries. Others proposed that something was blocking the light from distant stars. Maybe clouds of gas and dust absorbed the radiation before it reached us. The dust hypothesis was popular for a while, but it has a fatal flaw. If dust clouds were constantly absorbing starlight, they'd heat up tremendously. Eventually, they'd become so hot that they'd start radiating just as much energy as they were absorbing. You'd end up with glowing dust clouds everywhere, and you'd still have a bright sky. The problem wouldn't be solved, it would just be shifted to a different source. What about the idea that stars haven't been shining forever? Maybe the universe is old, but not infinitely old. If stars only started shining a finite time ago, then light from the most distant stars simply hasn't had time to reach us yet. That would explain some of the darkness. This was actually getting closer to the truth. But nobody in the 1800s had quite enough information to put all the pieces together. They were missing something absolutely crucial, something that wouldn't be discovered until the early 20th century. The breakthrough came from an unexpected direction. It wasn't a telescope observation or a mathematical proof. It was the realization that the universe itself isn't static. It's not frozen in place like a snapshot. It's dynamic, changing, evolving, and most shockingly of all, it's expanding. This discovery completely transformed how we understand everything. Space itself is stretching, carrying galaxies along with it like raisins in rising bread dough, and this expansion provides the key to unlocking Olbers Paradox. But before we get to how expansion solves the paradox, we need to understand what expansion actually means, because it's not what most people think. Galaxies aren't flying through space like rockets. That's a common misconception. Instead, new space is being created between galaxies. The fabric of space itself is stretching. Think of it like drawing dots on a balloon and then inflating it. The dots aren't moving across the surface of the balloon. The rubber between them is expanding, carrying them apart. That's what's happening in the universe, except in 3 dimensions instead of 2. The story of how we discovered cosmic expansion is absolutely fascinating, and it involves some of the most brilliant minds of the 20th century. It starts with a Belgian priest and physicist named Georges Lemaitre. In 1927, Lemaitre proposed something radical based on Einstein's general relativity equations. He suggested that the universe wasn't static at all. It was expanding from what he called a primeval atom. Most scientists, including Einstein himself, initially rejected this idea. Einstein was so convinced the universe had to be static that he'd actually added a mathematical fudge factor called the cosmological constant to his equations just to keep the universe from collapsing or expanding. Later, he'd call this his biggest blunder. Spoiler alert, the cosmological constant actually turns out to be important after all, but for completely different reasons we'll get to later. Around the same time, an American astronomer named Edwin Hubble was making observations at the Mount Wilson Observatory in California, using what was then the world's largest telescope. Hubble was studying distant galaxies, though back then many astronomers still called them spiral nebulae because they weren't sure these objects were separate galaxies or just clouds within our own Milky Way. Hubble made 2 groundbreaking discoveries. First, he proved that these spiral nebulae were indeed separate galaxies, vast collections of billions of stars lying far beyond the boundaries of the Milky Way. The universe was suddenly much, much larger than anyone had imagined, but his second discovery was even more shocking. Hubble noticed something peculiar in the light coming from these distant galaxies. When you split light into its component colors using a prism or a spectrograph, you get what's called a spectrum, basically a rainbow showing all the different wavelengths present in that light. Within that spectrum, you can see dark lines at specific positions. These lines are like fingerprints created when elements like hydrogen, helium, or oxygen absorb certain wavelengths of light. Here's where things get interesting. Hubble noticed that for distant galaxies, these spectral lines weren't where they should be. They were shifted toward the red end of the spectrum, toward longer wavelengths. This phenomenon is called redshift. Now, redshift happens because of something called the Doppler effect. You've experienced this with sound. When an ambulance approaches you with its siren blaring, the pitch sounds higher. As it passes and moves away, the pitch drops lower. The siren itself isn't changing. It's the motion that affects how you perceive the sound waves. When the source moves toward you, waves get compressed. When it moves away, they get stretched out. Light works the same way. When a light source moves toward you, its waves get compressed towards shorter, bluer wavelengths. That's called blue shift. When it moves away, the waves get stretched toward longer, redder wavelengths. That's redshift. Hubble found that nearly every galaxy he observed showed redshift. They were all moving away from us. But here's the kicker. The farther away a galaxy was, the faster it appeared to be receding. This relationship between distance and recession speed became known as Hubble's law. At first glance, this might make you think we're at the center of the universe, with everything fleeing from us like we've got cosmic bad breath. But that's not what's happening at all. Imagine you're an ant standing on one of those dots we drew on the balloon earlier. As the balloon inflates, every other dot moves away from you. But here's the crucial part. An ant standing on any other dot would see exactly the same thing. From every vantage point in the universe, it looks like everything else is moving away from you. This is what we mean by cosmic expansion. Space itself is expanding, and galaxies are being carried along with that expansion. The universe isn't expanding into anything, it's expansion itself. There's no edge, no center, no outside. It's expansion happening everywhere, all at once. By 1929, Hubble had gathered enough data to demonstrate this expansion convincingly. The implications were staggering. If the universe is expanding now, that means it was smaller in the past. Wind the clock back far enough, and you reach a point where everything was compressed into an incredibly hot, dense state. Lemaitre's primeval atom was looking more and more like reality. This idea eventually became known as the Big Bang theory. Though that name was actually coined by a skeptic, the astronomer Fred Hoyle used it mockingly during a radio broadcast in 1949. The name stuck, even though it's kind of misleading. The Big Bang wasn't an explosion in space, it was an explosion of space. It wasn't something that happened somewhere, it happened everywhere simultaneously. Current observations tell us the Big Bang occurred approximately 13.8 billion years ago. That's when time, space, matter and energy all came into existence together. Before that? Well, the question itself might not even make sense. What does before mean when time itself doesn't exist yet? Now, here's where we finally start to solve Olbers Paradox. The fact that the universe has a finite age, 13.8 billion years, means that we can only see light from objects that are close enough for their light to have reached us in that time. There's a cosmic horizon, a limit to what we can observe, simply because light hasn't had enough time to travel from more distant regions. If you're located somewhere in the universe, the farthest you can see is roughly 13.8 billion light-years in any direction, though the actual distance is more complicated because space has been expanding while that light traveled. We call this boundary the observable universe. Beyond that horizon, there's almost certainly more universe out there, possibly infinitely more. But we can't see it, and we never will, because the light from those regions hasn't reached us yet, and for reasons we'll get to, may never reach us. So that's part of the answer. Space is dark partly because the universe has a finite age, which means we can only see a finite number of stars and galaxies, even if the universe itself might be infinite. But wait, there's more to this story. The finite age of the universe helps explain some of the darkness, but it's not the complete picture. Even with the limited number of galaxies we can see within our observable universe, there are still 200 billion trillion stars out there. That's an almost incomprehensible number. Shouldn't all that starlight still make space pretty bright, even if we can't see infinitely far? This is where the expansion of the universe plays an even more critical role. And here's where things get truly mind-bending. The expansion isn't just carrying galaxies away from each other. It's fundamentally changing the light itself as it travels through space. Remember how we talked about redshift earlier? When astronomers first observed it, they interpreted it as a Doppler shift caused by galaxies moving through space. But as our understanding deepened, we realized something more profound was happening. The redshift we see from distant galaxies isn't just because they're moving away. It's because the space between us and them is expanding, stretching the light waves as they travel. Imagine a photon, a particle of light, leaving a distant galaxy billions of years ago. As that photon journeys through space toward Earth, the universe is expanding the entire time. The photon's wavelength gets stretched along with space itself. The farther the photon has to travel, and the longer it takes, the more stretching occurs. Light that left a distant galaxy as high-energy ultraviolet radiation might arrive at Earth as lower-energy visible light. Light that started as visible might arrive as infrared. and light from the most distant objects we can observe has been stretched so dramatically that it arrives as microwave radiation, completely invisible to our eyes. This is called cosmological redshift, and it's distinct from the Doppler redshift caused by actual motion through space. It's the expansion of space itself that stretches the light, and this stretching has profound implications for Olbers paradox. You see, when light gets redshifted, it loses energy. A photon's energy is inversely proportional to its wavelength. Shorter wavelengths mean more energy, longer wavelengths mean less energy. As the universe expands and stretches light to longer wavelengths, that light becomes less energetic. The most distant galaxies, the ones whose light has been traveling for billions of years through expanding space, have their light redshifted so dramatically that it becomes extremely faint. In fact, some of the most distant light in the universe has been redshifted all the way into the microwave part of the spectrum. This is the famous cosmic microwave background radiation, the afterglow of the Big Bang itself. This radiation fills all of space, coming from every direction, but we can't see it with our eyes because it's been stretched to wavelengths far too long for human vision to detect. If you could see microwaves, the sky would indeed glow uniformly in all directions. It wouldn't be dark at all. It would be filled with this faint uniform glow with a temperature of about 2.7 degrees above absolute zero. In a sense, Olbers was right that the sky should be glowing. It is glowing, just at wavelengths we can't see without special instruments. This cosmic microwave background was actually predicted before it was discovered. In 1948, physicists Ralph Alpher and Robert Herman calculated that if the Big Bang theory was correct, there should be leftover radiation from the hot early universe, cooled down and redshifted by billions of years of cosmic expansion. They predicted it would have a temperature of about 5 degrees above absolute zero for almost 2 decades. Nobody took this prediction seriously enough to actually look for it. Then in 1964, 2 radio astronomers named Arno Penzias and Robert Wilson were testing a sensitive radio antenna at Bell Labs in New Jersey. They kept detecting an annoying background hiss no matter where they pointed their antenna. They thought maybe it was interference. Maybe pigeon droppings were contaminating their equipment. They cleaned everything meticulously, but the signal persisted. It turned out they'd accidentally discovered the cosmic microwave background. This uniform glow, coming from all directions in space, was the cooled-down remnant of the Big Bang itself. Penzias and Wilson won the Nobel Prize in Physics for this discovery in 1978. The cosmic microwave background is one of the most important discoveries in all of cosmology. It's our baby picture of the universe, showing us what conditions were like when the universe was only about 380,000 years old, a cosmic infant compared to its current age of 13.8 billion years. At that time, the universe had cooled enough for atoms to form for the first time. Before then, it was too hot. Electrons couldn't stick to atomic nuclei because they had too much energy. The universe was an opaque plasma, kind of like being inside a glowing fog. Light couldn't travel far because it kept scattering off all those free electrons, but when atoms formed, the universe became transparent. Light could suddenly travel freely through space. The cosmic microwave background is that first light stretched and cooled by billions of years of expansion. When we observe it today, we're literally looking at the surface of that opaque fog from the early universe, seeing back to the moment when light could first travel freely. Now, here's something incredible. Missions like NASA's Wilkinson Microwave Anisotropy Probe, launched in 2001, and the European Space Agency's Planck satellite, launched in 2009, have mapped this cosmic background radiation with extraordinary precision. These maps reveal tiny temperature variations, differences of only a few millionths of a degree, that represent the seeds of all cosmic structure we see today. Those tiny variations were regions where matter was slightly denser or slightly less dense. Over billions of years, gravity amplified these tiny differences. Denser regions attracted more matter, growing into the galaxies, galaxy clusters, and vast cosmic structures we observe throughout the universe today. So we've established two major reasons why space is dark, despite being filled with stars. First, the universe has a finite age, limiting how far we can see. Second, cosmic expansion redshifts light from distant objects, draining its energy and often shifting it beyond the visible spectrum entirely. But there's actually a third factor at play, and it's perhaps the strangest and most unsettling aspect of cosmic expansion. Not only is the universe expanding, it's accelerating. The expansion rate is getting faster over time, and this acceleration has profound consequences for the darkness of space. The story of how we discovered this acceleration is fascinating. In the late 1990s, two independent teams of astronomers were studying distant supernovae, specifically a type called Typia supernovae. These stellar explosions are incredibly useful for cosmology because they're what we call standard candles. They all reach roughly the same peak brightness, so by measuring how bright they appear from Earth, we can calculate how far away they are. Both research teams, the Supernova Cosmology Project led by Saul Perlmutter and the High-Z Supernova Search Team led by Brian Schmidt and Adam Reyes, were trying to measure how much the expansion of the universe was slowing down over time. Everyone expected it to be slowing. After all, gravity pulls everything together, so it should be acting as a brake on the expansion. But in 1998, both teams announced something completely unexpected. The distant supernovae were dimmer than they should be, meaning they were farther away than expected. The universe wasn't slowing down at all, it was speeding up. This discovery was so shocking that both teams initially thought they must have made a mistake. They checked and rechecked their data, looking for errors. But the conclusion kept staring them in the face. Cosmic expansion is accelerating. Something is pushing the universe apart with increasing force, overpowering gravity's pull. But what could possibly cause this? The teams called it dark energy because, well, we have no idea what it actually is. It's dark because it doesn't emit, absorb, or reflect light. It's energy because it affects the expansion of space. Beyond that, dark energy remains one of the deepest mysteries in all of science. Here's what we know. Dark energy appears to be a property of space itself. As the universe expands and creates more space, there's more dark energy, which pushes even harder, accelerating the expansion further. It's like a cosmic feedback loop. The best current measurements suggest that dark energy makes up about 68% of all the energy and matter in the universe. Ordinary matter, the stuff that makes up stars, planets, and us, accounts for less than 5%. The remaining 27% is another mysterious substance called dark matter, which we can detect through its gravitational effects, but can't see directly. Think about that for a moment. We understand less than 5% of what the universe is made of. 95% of the cosmos consists of things we've named, but don't really understand. It's humbling and exhilarating at the same time. Perlmutter, Schmidt, and Reyes won the Nobel Prize in Physics in 2011 for their discovery of cosmic acceleration. Their work fundamentally changed our understanding of the universe's past and future. Now, how does accelerating expansion relate to why space is dark? Here's where it gets really interesting and a bit unsettling. As the expansion accelerates, distant galaxies are being carried away from us faster and faster. Eventually, they're receding so quickly that their light becomes redshifted into invisibility. Even more dramatically, there will come a time when galaxies beyond a certain distance are moving away from us faster than the speed of light. Wait, doesn't that violate Einstein's theory of relativity? Doesn't that theory say nothing can travel faster than light? Actually, no. What relativity says is that nothing can travel through space faster than light, but space itself can expand at any rate whatsoever. There's no speed limit on the expansion of space. Imagine ants crawling on the surface of our expanding balloon again. Even if each ant is crawling at a reasonable speed across the rubber, if the balloon expands fast enough, two ants on opposite sides can end up separating faster than either one is actually moving. The expansion of the medium, the rubber, can create separation speeds that exceed the individual motions. This means there are galaxies out there right now whose light will never ever reach us. They're beyond what's called the cosmic event horizon. Even though those galaxies exist, even though they contain hundreds of billions of stars, their light is fighting a losing battle against the expansion of space. They're disappearing from our observable universe, fading into permanent darkness. In fact, as time goes on, more and more galaxies will cross this horizon and vanish from view. Billions of years from now, if there are astronomers looking up at the sky from Earth, or whatever world exists then, they'll see far fewer galaxies than we can see today. The universe will appear darker and emptier. Eventually, trillions upon trillions of years in the future, the only galaxies remaining visible will be those in our local gravitationally bound group. The Milky Way, Andromeda, and a few dozen smaller galaxies will merge over time into one enormous galaxy, and beyond that, nothing but darkness. Future civilizations, if they exist, might look out and see only their own galaxy surrounded by complete blackness. They might conclude they live in a small, isolated universe surrounded by infinite void, never knowing about the vast cosmos that once filled the sky. It's sobering to realize that we live in a special time in cosmic history. We can still see the afterglow of the Big Bang. We can observe galaxies billions of light years away. We can piece together the history and structure of the universe. Future astronomers won't have that luxury unless we leave them detailed records of what we've discovered. Now let's step back and appreciate the complete answer to Olbers' paradox. Why is the night sky dark if the universe contains so many stars? First, the universe has a finite age. We can only see light from objects whose light has had time to reach us in the 13.8 billion years since the Big Bang, even if space extends infinitely in all directions, and it might, there's a horizon to our observations. Beyond that horizon, there simply hasn't been enough time for light to arrive. Second, the universe is expanding, and this expansion redshifts light from distant objects. The farther away something is, the more its light has been stretched to longer wavelengths and lower energies. Much of the light from distant galaxies has been redshifted right out of the visible spectrum, becoming infrared or even microwave radiation that our eyes cannot detect. Third, the expansion is accelerating. This means distant galaxies are receding faster and faster, making their light even more redshifted and faint. Some galaxies are already beyond our cosmic event horizon, permanently unreachable by any signal they send. Fourth, and this is something we haven't discussed in detail yet, there's also simple, old-fashioned absorption. Space isn't completely empty. Between the stars, there are thin clouds of gas and dust. Over vast distances, this interstellar medium can absorb and scatter light, dimming the brightness of distant objects. In Olbers' time, this seemed like a possible solution to the paradox, but it doesn't actually work in an infinite, eternal universe. The dust would eventually heat up from absorbing all that starlight and start glowing itself, contributing to a bright sky rather than solving the problem. But in our actual universe, finite in age, expanding and accelerating, the combination of all these factors explains the darkness beautifully. Space is dark, not because there aren't enough stars, but because of the fundamental nature of space and time itself. There's something poetic about this. The darkness of the night sky isn't just an absence, it's information. It tells us the universe had a beginning. It tells us space itself is dynamic, expanding and evolving. Every dark patch between the stars is evidence of the Big Bang, of cosmic expansion, of the finite speed of light. The darkness is a message written in the structure of the cosmos itself. Let's think about this from another angle. If you could somehow see all wavelengths of electromagnetic radiation at once, not just visible light, but infrared, ultraviolet, X-rays, gamma rays, radio waves, microwaves, would space still look dark? Actually, no. The sky would be filled with light. The cosmic microwave background would create a uniform glow in all directions. Distant galaxies invisible in visible light would blaze brightly in infrared. High-energy phenomena like quasars, black hole accretion disks, and supernova remnants would light up in X-rays and gamma rays. Pulsars and active galactic nuclei would shine in radio waves. Our eyes evolved to see only a narrow slice of the electromagnetic spectrum, the wavelengths that happen to be most abundant from our Sun and that pass through Earth's atmosphere effectively. This visible light window runs from about 390 nanometers, violet, to 700 nanometers, red. It's less than 1 octave of frequency, a tiny fraction of the full electromagnetic spectrum that spans many dozens of octaves from the longest radio waves to the shortest gamma rays. We're essentially looking at the universe through a narrow slit in a vast curtain. Most of the light is invisible to us, not because it isn't there, but because our biology didn't evolve to detect it. Birds can see into the ultraviolet, snakes can sense infrared, but humans are limited to that narrow visible band, and so we experience space as dark. Modern astronomy has changed this completely. We've built instruments that let us see the invisible universe. Radio telescopes detect the longest wavelengths. Infrared observatories pierce through cosmic dust to reveal hidden stars and galaxies. X-ray satellites observe the most violent phenomena in the universe: black holes tearing apart stars, neutron stars colliding, gas heated to millions of degrees. Gamma-ray telescopes detect the most energetic explosions in the cosmos. Each wavelength reveals a different universe. A radio map of the sky looks completely different from a visible light photograph, which looks different from an X-ray image. It's like having multiple sets of eyes, each revealing hidden layers of reality. One of the most remarkable instruments ever built is the Hubble Space Telescope, launched in 1990 and still operating today. By placing a telescope above Earth's distorting atmosphere, Hubble has given us unprecedented views of the universe. One of its most famous observations is called the Hubble Deep Field. In 1995, astronomers pointed Hubble at a tiny, seemingly empty patch of sky, a region about the size of a grain of sand held at arm's length. This area appeared completely black to ground-based telescopes, devoid of any visible stars or galaxies. Hubble stared at this empty patch for 10 days straight, collecting every possible photon of light. The result was stunning. That tiny patch of apparently empty space contained about 3,000 galaxies. Not 3,000 stars, 3,000 galaxies, each containing billions or hundreds of billions of stars. These galaxies were so distant and faint that we'd never detected them before. Some of them were among the most distant objects ever observed, their light having traveled for billions of years to reach us. Later, in 2003 and 2004, Hubble performed an even deeper observation called the Hubble Ultra Deep Field, revealing about 10,000 galaxies in an even tinier patch of sky. And in 2012, the Hubble Extreme Deep Field combined data from multiple observations to peer even farther back in time, revealing some of the earliest galaxies that formed in the universe. These deep field observations fundamentally changed how we think about the emptiness of space. Everywhere we look, no matter how dark a region appears, it's filled with galaxies stretching back through cosmic time. if we could see faint enough in every direction, we'd see galaxies upon galaxies upon galaxies, layer after layer receding into the past. So in a very real sense, Olbers' intuition was correct. Everywhere we look, our line of sight does eventually hit a star or galaxy. The universe is extraordinarily full of light-emitting objects. But because of the finite age of the universe and cosmic expansion, that light arrives so redshifted and faint that the sky appears dark to our eyes. Now you might be wondering, what about the future? We've talked about how the accelerating expansion will eventually carry distant galaxies beyond our cosmic horizon, making them disappear from view. But what else does the far future hold? Will the night sky get darker and darker? The answer, unfortunately, is yes. As dark energy continues to accelerate the expansion of space, the observable universe will shrink in terms of what's actually visible to us. Galaxies will fade and disappear as they cross our cosmic event horizon. Even the cosmic microwave background radiation will become increasingly redshifted and diluted. Within our local group of gravitationally bound galaxies, things will be different. The Milky Way and Andromeda galaxy are actually moving toward each other and will collide and merge in about 4 billion years. When this happens, it'll be a spectacular event, though individual star collisions will be rare because stars are so small compared to the vast spaces between them. The night sky during this merger will be absolutely stunning, with two galactic cores visible, massive bursts of star formation lighting up vast nebulae, and a dramatically transformed stellar landscape. After the merger settles down, we'll be left with one enormous elliptical galaxy that astronomers have playfully nicknamed Milkomeda or Milkdromeda. The dozen or so smaller galaxies in our local group will also gradually merge into this structure over hundreds of millions or billions of years. But beyond Milkomeda, nothing but darkness. Every other galaxy will have receded beyond our cosmic horizon, their light redshifted into undetectability. The cosmic microwave background will fade away. Any astronomers living in Milkomeda trillions of years from now will look out and see only their own galaxy surrounded by endless blackness. Unless they have access to astronomical records from our era, they might never know that the universe was once filled with hundreds of billions of galaxies. They might develop completely different theories about the nature of reality, theories constrained by the limited observational evidence available to them. They might conclude that Milkomeda is the entire universe, alone in an infinite void. This is actually a profound philosophical point. What we can observe about the universe depends on when we exist. The universe looks different at different epochs. There are things we can see today that will be forever hidden from future observers. And conversely, there may have been things visible to observers in the early universe that we can no longer see. It makes you wonder, what are we missing? What truths about the cosmos are already hidden from us because we weren't around early enough to observe them? What evidence has already been carried beyond our cosmic horizon, leaving us incomplete information about the true nature of reality? Some physicists find this deeply troubling. The idea that the universe might hide crucial information from us simply because of when we happen to exist seems almost unfair. But that's how it is. We're embedded in time, and time is embedded in the evolving structure of the universe. We can only see what our cosmic moment allows us to see. Despite these limitations, we've managed to piece together an astonishingly detailed picture of cosmic history. Let me walk you through the universe's biography, from birth to the present, and then into the far future. It all begins with the Big Bang, about 13.8 billion years ago. This wasn't an explosion in space. It was the expansion of space itself, beginning from an initial state of unimaginable density and temperature. In the first fraction of a second, the universe underwent a period of exponential expansion called cosmic inflation. growing from subatomic size to potentially larger than what's currently observable, all in less than a trillionth of a trillionth of a trillionth of a second. During these first moments, the universe was far too hot for atoms to exist. It was a seething plasma of fundamental particles and radiation. As it expanded, it cooled. Within the first few minutes, atomic nuclei began to form through a process called Big Bang nucleosynthesis, mostly hydrogen and helium, with traces of lithium. This primordial mixture matches what we observe in the oldest stars, providing beautiful confirmation of the Big Bang model. For the next few 100,000 years, the universe remained opaque, too hot for atoms to form. Finally, when it cooled to about 3,000 degrees, cooler than the surface of the Sun, electrons could combine with atomic nuclei without immediately being blasted apart by radiation. This era is called recombination, though that's actually a misnomer since electrons and nuclei were combining for the first time, not recombining. At this moment, the universe became transparent. Light could travel freely. This is the light we now detect as the cosmic microwave background, cooled and redshifted by billions of years of expansion from 3,000 degrees down to just 2.7 degrees above absolute zero. Then came the cosmic dark ages. With no stars yet formed, the universe was filled with neutral hydrogen gas, dark and featureless. Gravity began pulling matter together in the regions that had been slightly denser, guided by the invisible gravitational scaffolding of dark matter. Over millions of years, these density fluctuations grew into the first structures. About 100 to 400 million years after the Big Bang, the first stars ignited. These were nothing like our Sun. They were massive, perhaps hundreds of times the mass of the Sun, and incredibly hot and bright. They burned through their nuclear fuel in just a few million years before exploding as supernovae. These explosions forged the first heavy elements: carbon, oxygen, nitrogen, silicon, iron, and scattered them into space, seeding the universe with the raw materials needed for planets and eventually life. These first stars marked the end of the cosmic dark ages and the beginning of what astronomers call the epoch of reionization. The intense ultraviolet radiation from these early stars began ionizing the neutral hydrogen that filled space, stripping electrons away from the atoms. Over hundreds of millions of years, the universe transformed from neutral and opaque to ionized and transparent once again, but transparent in a different way than during recombination. As more generations of stars formed, lived, and died, they progressively enriched the universe with heavy elements. Astronomers call everything heavier than hydrogen and helium metals, even though this includes elements like carbon and oxygen that chemists wouldn't classify as metals at all. This terminology confuses everyone at first, but it stuck. Each generation of stars contributed more metals to the cosmic mix. The first galaxies began forming from the gravitational collapse of dark matter and gas. These early galaxies were small and irregular, colliding and merging to form larger structures. Supermassive black holes grew in the centers of many galaxies, powering brilliant quasars that outshone entire galaxies. Our own Milky Way galaxy formed through this process of mergers and accretion. It's still ongoing. We can see smaller satellite galaxies orbiting the Milky Way, and we know from stellar archaeology that our galaxy has cannibalized many smaller galaxies over its history. The stars from those absorbed galaxies are now part of the Milky Way's halo and disk, their original galactic homes long since destroyed. About 9 billion years after the Big Bang, roughly 4.6 billion years ago, in one spiral arm of the Milky Way, a cloud of gas and dust began to collapse under its own gravity. This was the birth of our solar system. Most of the material fell into the center, igniting to become our Sun. The remaining material formed a disk that gradually coalesced into planets, asteroids, and comets. The third planet from the Sun, Earth, formed in the so-called habitable zone, where temperatures would allow liquid water to exist on the surface. Early Earth was a hellish place, bombarded by asteroids, covered in molten rock, with an atmosphere of carbon dioxide and nitrogen, but it cooled, water condensed, oceans formed, and somehow, we still don't fully understand how chemistry became biology. The first simple cells appeared about 3.8 billion years ago. For most of Earth's history, life consisted only of single-celled organisms. Then, about 600 million years ago, complex multicellular life exploded in diversity. Animals, plants, fungi, the incredible variety of life we see today, all descended from those early experiments in multicellularity. And then, just 200,000 years ago, an eye blink in cosmic time, our species, Homo sapiens, emerged in Africa. For most of human history, we looked up at the stars and wondered what they were. Gods? Spirits? Tiny holes in the celestial sphere, letting divine light shine through? Only in the last few centuries have we begun to understand the true nature of the cosmos. We discovered that Earth orbits the Sun, that the Sun is a star like countless others, that stars are organized into galaxies, that galaxies are organized into clusters and superclusters, that the entire universe is expanding from a hot, dense beginning. We live in an extraordinary moment. We're the first generation of humans with telescopes powerful enough to see the cosmic microwave background, to observe galaxies billions of light years away, to piece together the history of the universe from the Big Bang to the present. Our ancestors looked at the dark night sky and created myths. We look at the same dark sky and see evidence of cosmic evolution, of the finite speed of light, of space itself expanding, and that darkness, that beautiful, mysterious darkness between the stars, tells us all of this. It's not empty or meaningless. It's full of information about where we came from and where we're going. But let's continue the story into the future. What happens next? Our Sun is currently about 4.6 billion years old, roughly halfway through its main sequence lifetime. For another 5 billion years or so, it will continue fusing hydrogen into helium in its core, providing steady energy to Earth. But eventually, the hydrogen fuel will run out. When that happens, the Sun's core will contract and heat up, while its outer layers expand dramatically. The Sun will become a red giant, swelling to perhaps 100 times its current diameter. It will likely engulf Mercury and Venus, and possibly Earth as well. Even if Earth's orbit isn't completely absorbed, the planet will be baked to a lifeless cinder, its oceans boiled away, its atmosphere stripped off. After about 1 billion years as a red giant, the Sun will shed its outer layers in a beautiful planetary nebula, one of those gorgeous cosmic clouds you see in astronomical photographs. The core will remain as a white dwarf, a dense object about the size of Earth but containing about half the Sun's mass. This white dwarf will slowly cool over trillions of years, eventually fading to a black dwarf, a cold, dark cinder emitting no light. But long before the Sun dies, other dramatic changes will occur. Remember that collision between the Milky Way and Andromeda. That begins in earnest around 4 billion years from now. The night sky will transform as Andromeda looms larger and larger, eventually filling much of the sky. During the merger, gravitational interactions will fling some stars into intergalactic space while driving others into new orbits. Our solar system will likely survive this collision relatively unscathed. Space is so vast that direct collisions between stars are extraordinarily unlikely. But we'll end up in a completely different location within the merged galaxy, possibly far from the galactic core or even flung into the outer halo. The merger will trigger massive bursts of star formation as gas clouds collide and compress. For a few 100 million years, Milkomeda will be a starburst galaxy, blazing with the light of billions of newly formed stars. Then, as the available gas is used up, star formation will gradually decline, and as we discussed, everything beyond our local group will fade from view. The night sky of Milkomeda will be spectacular in the short term, filled with star clusters, nebulae, and the combined light of two merged galaxies. But it will be lonely. No other galaxies will be visible. The universe beyond will be hidden behind an expanding cosmic horizon. Let's push even further into the future, into timescales that become almost incomprehensible. Trillions of years from now, the last stars in Milkomeda will flicker and die. Star formation requires gas, and eventually all the available gas will either be locked up in stars, planets, and stellar remnants, or will be too dispersed and hot to collapse under gravity. The era of star formation will end. The universe will enter what's called the degenerate era. The only objects shining will be the slowly cooling remnants of dead stars, white dwarfs, neutron stars, and black dwarfs. These will provide dim light for an unimaginably long time. A white dwarf cools extremely slowly because it's so dense and has no internal energy source. It will take longer than the current age of the universe for a white dwarf to cool to the temperature of the cosmic microwave background. But even these will eventually fade. Given enough time, even the most stable structures will decay. Protons themselves might not be stable forever. If protons decay, which is theoretically possible but has never been observed, then all ordinary matter will eventually disintegrate into radiation and lighter particles. Planets, dead stars, even black holes orbiting through the void, all will gradually evaporate. We enter the black hole era. After proton decay has dismantled ordinary matter, black holes will be among the last remaining objects. They seem eternal, but Stephen Hawking discovered that they're not. Black holes emit radiation through quantum effects near their event horizons, a process called Hawking radiation. This causes them to slowly lose mass and eventually evaporate completely. The rate of evaporation depends on the black hole's mass. Smaller black holes evaporate faster. A black hole with the mass of the Sun would take trillions of years to evaporate. Supermassive black holes, like the one at the center of our galaxy, containing millions or billions of solar masses, would take incomprehensibly longer. When a black hole finally evaporates completely, it ends in a final burst of radiation and disappears. After this process has run its course for every black hole in the universe, we enter the final era, the dark era. The universe has reached maximum entropy. All structure has dissolved. All energy has been dispersed as evenly as possible. The temperature has cooled to just barely above absolute zero. Space is filled with a thin soup of photons, neutrinos, and other fundamental particles, all moving away from each other as space continues to expand. Nothing happens. Nothing can happen. There's no energy gradient to drive any processes. The universe is dead, not in the sense of being destroyed, but in the sense of being unable to change. This is the heat death of the universe, the final equilibrium state predicted by thermodynamics. How long does this last? Forever. The dark era has no end. The universe continues expanding into the infinite future, becoming ever more dilute, ever colder, approaching but never quite reaching absolute zero. It's a bleak picture, isn't it? Everything we know, stars, planets, galaxies, life, represents a brief period of structure and complexity in the universe's history. We exist during a cosmically special time, when the universe is old enough to have formed stars and planets and complex chemistry, but young enough that stars still shine and galaxies still cluster. But even this dark future might not be the whole story. Our understanding of physics is incomplete. We don't fully understand dark energy, dark matter, quantum gravity, or the ultimate nature of space and time. There might be phenomena we haven't discovered yet that could change the far future in ways we can't predict. Some physicists have speculated about even more exotic possibilities. Maybe the expansion will eventually reverse, causing a big crunch where the universe collapses back on itself. Maybe the accelerating expansion will tear apart all structure in a big rip, literally ripping atoms apart. Maybe there are cycles of expansion and contraction. Maybe our universe is one of countless others in a vast multiverse. We don't know. What we do know is that we live in a universe governed by physical laws we can understand, at least partially. And those laws allow for the existence of stars, planets, and beings capable of asking questions about their own existence. Let me bring this all back to where we started. Why is space dark? We've covered an enormous amount of ground. We've talked about the finite age of the universe, the expansion of space, redshift, cosmic horizons, the Big Bang, cosmic evolution, and the ultimate fate of everything. All of this connects back to that simple observation that puzzled Olbers centuries ago. The darkness of space is a consequence of the universe having a history. If the universe were infinite, eternal, and static as people once believed, the night sky would indeed be blazingly bright. But our universe is none of those things. It had a beginning, it's expanding, it's evolving. Every dark patch between the stars is evidence of the Big Bang. It tells us that light has a speed limit and the universe has an age. It tells us that space itself is dynamic, not static. It tells us we're living in a particular epoch of cosmic history, neither at the beginning nor at the end, but in a middle period when stars shine and galaxies dance through space. The darkness is also a gift. Without it, life as we know it couldn't exist. The dark vacuum of space acts as insulation between stars, allowing planetary systems to have their own temperature regimes determined primarily by their host star. If space were filled with intense radiation from all directions, planets would be baked by a constant, overwhelming glare. The darkness provides the cold background against which warm, life-bearing worlds can exist. And the darkness invites us to explore, to wonder, to ask questions. When early humans looked up at the dark sky punctuated by stars, they began the scientific journey that would eventually lead to our modern understanding of the cosmos. The mystery of the darkness drove us to build better telescopes, develop new physics, and ultimately discover that we're part of a vast, ancient, evolving universe. So space is dark because of the most fundamental properties of our universe: the finite speed of light, the finite age of time, and the expansion of space itself. The darkness is not empty nothingness. It's full of meaning, full of history, full of information about where we came from and where we're going. The darkness of space, then, is not a flaw or an absence. It's evidence of the universe's true nature. It's proof that we live in a dynamic, evolving cosmos with a definite beginning and a trajectory toward an uncertain future. Think about how extraordinary this is. When you look up at the night sky, you're looking back in time. The light from the nearest star, other than the sun, left over 4 years ago. Light from stars across the galaxy left decades, centuries, or millennia ago. Light from the Andromeda galaxy left 2.5 million years ago, when our ancestors were primitive hominids just learning to make stone tools. Light from distant galaxies left billions of years ago, when Earth was young, or perhaps before it even existed. The darkness between those pinpoints of light is not empty. It's filled with information about cosmic expansion, about the age of the universe, about the speed of light, about the fundamental nature of space and time. And here's something beautiful: you are made of stardust. Every atom in your body heavier than hydrogen was forged in the nuclear furnaces of ancient stars or in supernova explosions. The calcium in your bones, the iron in your blood, the carbon in your DNA, all of it was created by stars that lived and died billions of years ago. You are literally made from the cosmos, a way for the universe to know itself. When we talk about the darkness of space, we often imagine vast empty voids between galaxies. But modern astronomy has revealed something extraordinary. The darkness has structure. It's not uniformly empty. Instead, galaxies are arranged in an intricate cosmic web, a vast network of filaments, sheets, walls, and voids that extends across the entire observable universe. Imagine you could see the universe from an impossibly distant vantage point, looking down on billions of galaxies at once. What would you see? Not a random scattering of galaxies like stars sprinkled randomly across the sky. Instead, you'd see galaxies organized into threads and sheets surrounding enormous empty regions, like the foam in a bubble bath or the structure of a sponge. These filaments can be hundreds of millions of light-years long, containing thousands of galaxies strung along like beads on a cosmic string. Where filaments intersect, you find massive galaxy clusters containing thousands of galaxies bound together by gravity. And between these filaments, cosmic voids, vast regions hundreds of millions of light-years across that contain almost no galaxies at all. This structure formed through gravitational amplification of tiny density fluctuations in the early universe. Remember those quantum fluctuations we discussed earlier? Those microscopic variations in density that existed just after the Big Bang. As the universe expanded and cooled, gravity went to work on those variations. Denser regions attracted more matter, becoming denser still. Less dense regions lost matter to their denser neighbors, becoming emptier. Over billions of years, this process carved out the cosmic web. Dark matter, which makes up about 85% of all matter in the universe, played the crucial role. Dark matter doesn't emit, absorb, or reflect light, making it completely invisible. We can only detect it through its gravitational effects. But it was dark matter that provided the gravitational scaffolding on which galaxies formed. Here's something mind-bending. The dark matter structure formed first, like an invisible skeleton. Then ordinary matter, the stuff we can see, fell into the gravitational wells created by dark matter concentrations. Stars and galaxies formed where dark matter was densest. So when we look at the cosmic web of galaxies, we're really seeing the distribution of dark matter made visible by the ordinary matter it attracted. The voids between the filaments aren't completely empty, but they're remarkably vacant. If you were somehow placed in the middle of a cosmic void, the nearest galaxy might be 50 million light-years away in any direction. The night sky would be almost completely black, just a handful of faint, distant smudges of light scattered across the darkness. It would be one of the loneliest places in the universe. And here's something that should make you appreciate Earth's location. We live in a relatively dense part of the universe. The Milky Way is part of the local group, which sits on a filament called the local sheet, which is connected to the even larger Virgo supercluster, or as it's now called, we're on the outskirts of the Laniakea supercluster, a region containing about 100,000 galaxies. We have neighbors. The night sky is rich with visible galaxies and stars. A civilization evolving in a cosmic void might develop completely different cosmology. With no nearby galaxies to observe, they might never discover that galaxies exist beyond their own. They might think their galaxy was the entire universe. They could live in the 21st century equivalent of technology and still be cosmically ignorant simply because there's nothing nearby to observe. This raises a profound question. What are we missing? Are there features of the universe that we can't detect because they don't happen to exist in our observable region? Are there aspects of reality hidden from us by cosmic happenstance? Now let's talk about one of the most mysterious discoveries in all of physics, dark energy. In 1998, two independent teams of astronomers were studying distant supernovae, specifically Type Ia supernovae, which are stellar explosions that always reach approximately the same peak brightness. This makes them excellent standard candles for measuring cosmic distances. By comparing how bright they appear with how bright they actually are, you can calculate how far away they are. These teams were trying to measure how much the expansion of the universe was slowing down. Everyone expected that the expansion should be decelerating. After all, gravity is attractive. It should be pulling everything back together, slowing the expansion that began with the Big Bang. The question was just how much it was slowing. They found something completely unexpected. The expansion wasn't slowing down, it was speeding up. The universe's expansion has been accelerating for about the last 5 or 6 billion years. Distant galaxies aren't just moving away from us, they're moving away faster and faster. Something is pushing the universe apart, counteracting gravity on cosmic scales. Scientists called this mysterious something dark energy, but that's really just a label for our ignorance. We don't know what it is, we don't know where it comes from. We just know it exists because we can measure its effects. Dark energy makes up about 68% of the total energy content of the universe. Dark matter makes up about 27%. Ordinary matter, everything we can see, everything made of atoms, all the stars and planets and gas clouds, makes up only about 5% of the universe. We live in a universe dominated by things we don't understand. The accelerating expansion has profound implications for the darkness of space and the future of the universe. It means that galaxies beyond our local group will eventually accelerate away from us faster than light can travel through space. This doesn't violate relativity. Nothing is moving through space faster than light, but space itself is expanding between us and distant galaxies fast enough that light from those galaxies can never reach us. We discussed this earlier, but let me emphasize just how strange this is. There are galaxies that we can see right now, whose light is reaching us from the distant past. But due to the accelerating expansion, we will never be able to see what those galaxies look like now in their current state. By the time light from their current state could reach us, they'll have been carried beyond our cosmic horizon. In fact, we're constantly losing galaxies. Every moment, some galaxy crosses from observable to forever unobservable as the accelerating expansion carries it beyond the boundary from which light can ever reach us. The darkness of space is, in a sense, growing, not because lights are going out, though that will happen in the far future, but because the observable universe is actually shrinking in terms of how many galaxies we can potentially see. The darkness is reclaiming territory from the light. Imagine you're standing in a vast dark room with thousands of candles scattered around. Now imagine the room is expanding and the expansion is accelerating. Candles that you could see a moment ago are now being carried so far away that their light no longer reaches you. The darkness closes in, not from the candles extinguishing, but from the space between you and them growing too vast. That's happening to our universe right now. The darkness between galaxies is expanding, stretching, growing, and because this expansion is accelerating, more and more of the cosmos is being pushed beyond the horizon of what we can ever observe. Here's something that should keep you awake at night. We're living in an era of maximum cosmic knowledge. Future civilizations billions of years from now will know less about the universe than we do today. Why? Because of the accelerating expansion driven by dark energy. Right now, we can observe the cosmic microwave background, the afterglow of the Big Bang. We can measure its temperature, map its tiny fluctuations, and use it to understand the early universe. We can observe distant galaxies at various stages of cosmic history. We can see quasars from when the universe was young. All of this evidence allows us to piece together the history of the cosmos. But in the far future, say 100 billion years from now, all of this evidence will be gone. The cosmic microwave background will be redshifted to such long wavelengths and diluted to such low temperatures that it will be utterly undetectable. All galaxies beyond our local group will have been carried beyond the cosmic horizon by the accelerating expansion. They'll simply vanish from view, winking out one by one like lights being switched off. A civilization arising on a planet orbiting a star in our galaxy 100 billion years from now would look out into space and see Almost nothing. Just the stars of their own galaxy, actually by then, the merged Milky galaxy, surrounded by eternal darkness, no distant galaxies, no cosmic microwave background, no evidence of the Big Bang, no evidence of cosmic expansion. These future scientists, using telescopes far more advanced than ours, would observe a seemingly static, eternal universe consisting of a single galaxy island in an infinite dark sea. They might develop theories about how their galaxy formed, but they'd have no way to know about the Big Bang, about cosmic inflation, about the billions of other galaxies that once existed. That information would be literally unreachable, carried away by the expansion of space. Some of those future scientists might propose wild theories. Maybe there are other galaxies out there, beyond what we can see, but they'd have no evidence, no way to test their ideas. The truth about the universe's history would be hidden from them by the darkness. This raises an unsettling question. What is the darkness hiding from us right now? Are there aspects of the universe's history that we've already lost access to? Evidence that crossed beyond our cosmic horizon before we evolved to observe it? Entire eras of cosmic evolution that left no traces we can detect. We know, for instance, that cosmic inflation, that brief period of exponential expansion in the first fraction of a second after the Big Bang, stretched space so rapidly that regions that were once in contact with each other were pushed apart faster than light. The observable universe we see today originated from a region smaller than an atom, but the full universe created during inflation is vastly larger than what we can observe. There could be regions of space, now impossibly far away, where the laws of physics are different, where constants of nature have different values, where entirely different kinds of matter and energy exist. These regions would be forever beyond our observation, hidden by the ultimate darkness of an impassable cosmic horizon. Some physicists propose that we live in a multiverse, a vast ensemble of separate universes, each with potentially different properties. If this is true, those other universes are hidden from us by a darkness more profound than the darkness of space. They're causally disconnected, beyond any possible observation or interaction. The darkness, in this sense, represents the ultimate limit of knowledge. No matter how advanced our technology becomes, no matter how clever our theories, there are things we fundamentally cannot know because the information is hidden beyond horizons we can never cross. This is simultaneously humbling and exhilarating. Humbling because it reminds us that we're not at the center of everything, that we don't have access to complete knowledge of reality. Exhilarating because it means the universe is more vast and mysterious than we can possibly imagine. There are always new frontiers, new mysteries, new questions to ask.